Hello students, welcome to today's lesson. It's nice to have you on today's lesson. In today's lesson we shall be considering temperature. Well, this is a topic that is very short considering the Cambridge syllabus. But if I may ask you what temperature is all about, you will likely tell me that temperature is the degree of hotness of a system or a body. But the fact is that temperature is more than that. The definition of temperature is far more than what I've just said, because we can isolate temperature from a dependable factor that influences it, from a dependable factor that influences it himself. Okay, so at this point we shall be considering temperature as a whole, everything you need to know about temperature as far as the Cambridge syllabus is concerned. Well, if I may ask you this question, can there be temperature in the real sense without the application of heat? Is it possible for us to have temperature in the real sense, in reality, without the application of heat? Well, this is a question we just need to critically reason on and think about it. If I may respond to this question, I will say that it is capital no. There is no way we can isolate the application of heat in the application of temperature, because temperature depends on the level or amount. It depends on the level of heat that is supplied to a system or to a region or to a body. So because how hot or cold an object or region is on this ground, we can simply say temperature depends majorly on heat. But these have nothing to do with the magnitude of heat per se. Okay, we are not saying that temperature is the measurement of the amount of heat. We are still going to talk more on that later. But the fact remains that temperature depends on heat, and it is the level of heat supplied to a system that will determine the degree of hotness of that system. So based on what I've just said now, we can't talk of temperature without discussing heat. Though some do mistake temperature for heat, but the fact is that they are never the same. You need to get this point clear. Temperature and heat are never the same. Temperature only depends on heat, and more so, heat only influences or maintain temperature. So that's just it. That's the function of the heat there, is to influence the temperature, to determine the degree of hotness or to maintain the temperature. So if heat is withdrawn, it will definitely in a way affect the degree of hotness of a system. Okay, so temperature is different from heat completely. However, temperature depends on heat. So at this point, let's quickly take a look at the differences between heat and temperature. Then from the differences, we can now figure out the definition of temperature in whole, okay, as well as the definition of heat in whole. So let's quickly take a look at differences between heat and temperature. Well, one of the differences between heat and temperature is the fact that the measure of total vibrational energy of all molecules of a substance. This is heat per se. This is heat. Heat is the measure of total vibrational energy of all molecules of a substance. Okay, when you are considering a given body, be it solid, liquid, or gas, okay, each system, each body, or each state of matter consists of particles or atoms. And under ideal gas, you must have been taught, or you must have understand the fact that two or more atoms makes a molecule. Okay, so when we're having molecule in their numbers making up a substance, okay, the movement of that molecule tends to create a vibrational energy. Most especially, it is obvious in solid, okay, that we also have it in liquid as well as in gas, but it is more obvious in solid. Okay, so the molecules, they exhibit vibrational motion. Why? Because there is a kind of movement, okay, within a given point, around them, maintaining a given point. But if we are considering gas, then they exhibit a collision. Okay, there's a collision between one molecule and the other, or against the wall of the container, and that alone creates an amount of energy, okay, as a result of the movement around or in collision with the wall of the container. Now, the total energy exhibited by all the molecules in the system or in that substance is what we call the total vibrational energy. Okay, so the magnitude of that, what constitutes heat. Okay, now, but when we look at the temperature aspect, it is actually a measure, or the measure of average kinetic energy of all molecules of a substance. Average kinetic energy. In fact, this was proved and justified under ideal gas. When we use a Boltzmann constant, we are able to derive a relationship between the thermodynamic temperature of a gas as well as the average kinetic energy of the molecule of such a gas. Okay, so this is already being verified under ideal gas. So on this basis, temperature simply tells us the average kinetic energy of all molecules, not just one molecule, but all molecules of a substance, because by the time each molecule collide with the other molecule or with the wall of the container, there is a movement created, and that is a random movement. Okay, and the energy due to the movement of a particle or an atom or probably a molecule is called a kinetic energy. So the average of that is, the measure of the average of that kinetic energy gives us the temperature of the whole molecule of the system. Another second difference between heat and temperature is that heat is a form of energy which can be transferred between places at different temperatures. I take that again. It is a form of energy which can be transferred between places at different temperature. Okay, we can have a region of high temperature and have another region of lower temperature. Okay, now the transmission of energy from higher region to a lower region, okay, is as a result of the movement, or probably, let me say, a transfer of some certain amount of energy from the higher region to the lower region. Okay, and that is what is exhibited in water, in boiling water. Okay, when you place a water in a kettle and you place that on fire, you heat, or on Bunsen burner rather, okay, and heat is supplied. What you're going to notice for some second is that when you dip your finger at the top, at the surface of the water, you still feel the normal temperature of the water before being placed on the Bunsen burner. But when you dip your finger deep down to the bottom, you are going to notice that the temperature changes. The temperature at the bottom of the water is not as the same as the temperature at the surface of the water. The reason is because the bottom absorbs more heat because closer to the heat, and the top is still maintaining or have a relative different temperature compared to that of the bottom. So since the bottom part or the lower part of the kettle absorb more heat, definitely energy absorbed by the molecule in the lower region is not going to be the same, or in the bottom part is not going to be the same with those at the top, okay, or at the upper region of the water. So in that case, the molecules at the lower region will want to migrate from the lower part to the upper part, and as a result of that, they tend to saturate the top of the water as time goes by until the temperature becomes balanced and the water begins to boil. Okay, so what exactly happened there is that there is a form of transfer of energy from the lower region, which is of higher temperature, then to the upper region, which is of lower temperature. So this exactly explains it in its full sense, because the molecules in the lower region will want to escape to find a more convenient region to stay, and then it has to migrate to the top. And as that keeps on going, as more molecules are coming up, the water is getting saturated in terms of heat, and its temperature increases. But when we consider temperature from this angle, it is actually a degree or scale of hotness or coldness of a body, depending or showing the direction of flow of heat. Or let me put it like this, that depending on the direction of flow of energy. Okay, but meanwhile, the degree of hotness or coldness basically indicates the direction of flow of heat. Okay, that simply means that the direction from higher temperature to lower temperature tells us the direction of the flow of heat, that it is coming from a higher region of heat supply to a lower region, meaning that the one with higher temperature is actually having more internal energy, though we're still going to talk more on this, than the one at the lower region, the one of higher temperature is having more internal energy, then the one of lower temperature is having lesser internal energy. So energy is going to flow from the region where we have higher internal energy to the region of lower internal energy until the whole system is balanced. So this really tells us, so when you have a body that is cold and gradually the body starts getting hot or hotter, then what it simply means is that there is a flow of energy. Okay, there is a flow of energy due to energy supply. Okay, so these are the basic differences, the two basic differences between heat and temperature. Okay, now I need to say that the points raised here for either heat or temperature can also be used for defining them. We can use to define each of these terms. Okay, so the point I raised for temperature can be used to define the word temperature, while the points I raised for heat can be used to define the word heat, or the term it. So in case you come across this question in your exam or in any past question, this is exactly what they are requesting from you according to the mass scheme. Okay, so these are the salient point that must reflect in your definition. All right, from here, let's quickly see some evidence from everyday life which indicates that thermal energy always flow from high temperature to low temperature. I've explained that in a way that, of course, energy is always being transferred from region of higher temperature to region of lower temperature. But we want to see life experiences, everyday experiences, or everyday life event that actually justify this, or that can be served as an evidence or proof this fact that truly thermal energy flows from region of high temperature to region of low temperature. Okay, let's see the first example there. The first example we shall be looking at is considering a thick metal bar. If you just think about a thick metal bar with one end heated by pouring hot water over it. If you pour hot water over one end of a thick metal bar, and the other hand is cooled by holding it under a cold tap water, a cold water tap. Okay, what you are going to notice as time goes by is that you are going to feel a kind of sensation. There's going to be a kind of sensation between these two ends, and the sensation you are going to feel is actually another magnitude of temperature. Okay, knowing full well that the one end is of higher temperature and the other end is of a lower temperature because it's placed under cold water tap. Okay, so the sensation you're going to feel in between these two ends is actually the effect of the temperature difference. The difference in the temperature of the two ends, between the two ends. And actually the difference between the ends tells us that thermal energy is transferred along the bar from high temperature end to the low temperature end. Okay, that is just the justification that gives you that kind of sensation. Okay, so the effect of the temperature difference between the two ends, the hotter part and the colder part, is actually as a result of thermal energy that is being transferred along the bar from the high temperature end to the low temperature end. Okay, so let's see another evidence that helps to justify that thermal energy is transferred from higher temperature to lower temperature. Second evidence, think about an iron spoon, a metallic spoon placed on a hot cooking pot. If you place a metallic spoon on a hot cooking pot, okay, and leave it for some time, after some time that you've left it, come back to it and check up on it, you will notice that the iron spoon will have tapped some degree of hotness. Okay, why? Because there is a conduction of heat from the hot cooking pot to the iron spoon. Okay, so that the iron spoon is going to tap some amount of degree of hotness from the hot cooking pot. And the reason is simply because thermal energy is transferred from the high temperature, which is the hot cooking pot, to the low temperature, which is the iron spoon. Okay, that's just the implication. Okay, the sensation that is felt whenever the iron spoon is withdrawn from the hot cooking pot is actually because thermal energy is transferred from high temperature, which is the hot cooking pot, to the low temperature, which is the iron spoon. Now I need to say it, though I've said it before, but I need to re-emphasize this, that generally the outer part of the body or of an object loses internal energy. Okay, why the cooler part gains internal energy. So whenever energy is transferred from one region to another, what simply happens is that the region of higher temperature or the region that is hotter, okay, loses internal energy, while the region that is of lower energy or that is cooler gains the internal energy that was lost by that of the outer part. Okay, so you need to take note of this part. It's really very important. Now, what you shall never say temperature is. Okay, there are some things you can't say temperature is. Okay, basically let me just say that temperature cannot be defined in a particular way. Though some people, they have some kind of misconception, but the fact is that temperature are not what some people say it is. Okay, or the angle or the conceptual meaning they give to temperature. Okay, so we want to see what you should never say temperature is. Okay, we will be able to define temperature, and we will be able to relate between temperature and heat as well as the differences. Now we want to see what temperature is not. Okay, so this will give you a perfect understanding of temperature in hot. Okay, what you should never say temperature is. Alright, let's quickly have this. I need to tell you that temperature is never a measure of the amount of thermal energy, or you can simply say heat energy in a body. It's never, and it will never be a measure of the amount of thermal energy or heat energy in a body. There is a reason, because from observation we have seen that this cannot be justifiable. This cannot be justified. Okay, it can be justified from various observation, even in the laboratory. Okay, so you don't define temperature in terms of a measure of the amount of thermal energy. Though I said temperature depends on thermal energy, but it is not the magnitude, or let me put it like this, that it does not measure the quantity of thermal energy, okay, in a body system. Why do I say this? Or why do scientists come up with this? Okay, these are the reasons. Number one, two bodies of different masses at same temperature and of same material. Take note of those 2 points. I tell you again, two objects of different masses of same temperature. I need you to take note of that word, different masses. Like if we are having two different masses, okay, like 20 gram, another one is 50 gram, and those two masses are having same temperature, probably let's say they're having 30 degrees Celsius, okay, and they are also made of same material. They are as well made of same material. Okay, now I need you to know, and let it sink deep down in you, that they will have different amount of heat. They will have different amount of heat, irrespective of the size of the masses. Okay, as far, even if they have same temperature and are made of same material, they will still have different amount of heat. Okay, so this does not justify temperature. Because if temperature is truly the amount of heat, then it should be that different masses will have the same amount of heat, if truly. But in this case, we are saying that different masses will have different amount of heat, and they will still have same temperature. So how does that correlate? It doesn't correlate at all. So this alone has nullified the fact that temperature is temperature is a measure of amount of thermal heat. It has nullified that statement that temperature is a measure of the amount of heat. So in this case, you can define temperature in terms of amount of thermal energy. Another second reason is this: temperature shows direction of heat transfer from high to low region regardless of object. I've explained this the other time, that temperature gives us a sense of direction of how heat energy is transferred from high temperature region to lower temperature region regardless of the objects, okay, or regardless of the region. Okay, so this is just a fact. That's just a fact. It only tells us of direction, not in terms of magnitude. Alright, now let's quickly take a look at the third point right here. When substance or boils, there is no temperature change. Take note of that word. There is no temperature change, despite there is increase in heat supplied. Despite there is increase in heat supply. So if this simply means there are some substance that when they are at their melting point or they are at their boiling point, okay, temperature remains the same, whereas heat supply keeps increasing. So this alone again has justified the fact that temperature is never a measure of the amount of thermal energy. Because if it is, then when temperature is constant, the amount of thermal energy should also remain constant, not increasing. So temperature does not depend on the amount of energy. It does not depend on the amount, it does not measure. Let me put it that way. I need you not to confuse those two words. There are difference between depend and the difference between measures. Okay, so temperature actually depend, but temperature don't measure the amount of thermal energy. Okay, so from here, let's quickly consider another important part of temperature. And at this point in time, we need to consider thermal equilibrium, or you can simply say heat equilibrium. Thermal simply means heat. Okay, so thermal equilibrium. During the course of my explanation, I said the other time that temperature, okay, tells us the direction, okay, from which energy is actually being transferred. And I said energy is transferred from higher temperature to region of lower temperature. Okay, but at a point in time in every given substance, temperature seems to balance up. Okay, that is when transfer, okay, from the higher region to the lower region. At a point in time, the temperature of the two regions balances up. Okay, at that point when the two region balances or their temperature becomes the same, okay, at that point what happens is that the net transfer energy becomes zero. Why? Because the two bodies become saturated, okay, with the same temperature. Okay, and at that point in time, their total internal, the individual, let me put it that way so that you don't get confused, individual internal energy becomes the same too. Okay, so at that point, the other part wants to transfer energy, to the other one. The other one at the other hand also want to transfer the same set of energy to the other part. And so at a point in time, the two cancel out. So that means total or net internal energy or heat energy is zero. Okay, so at this point in time, from this concept, from the concept I've just explained, we can get the definition of thermal equilibrium. So the question is, what is thermal equilibrium? Based on the simple explanation I just gave now. Okay, let's quickly look at that. Thermal equilibrium occurs when different regions, I need you to take note of these keywords I'm highlighting. Okay, different region, not same region now. Okay, different regions or objects in thermal contact. The two regions must be in thermal contact, or probably the two objects must be in thermal contact. That is, they must be in contact with one another. So at the point when they are in contact with one another, okay, their temperature becomes the same. That temperature becomes the same. Don't forget where we are coming from. The first thing is that they are not the same at first. They are actually objects of different temperature. That's why I said different region or different objects. Okay, now because they come in thermal contact, they come in contact with themselves, so heat or energy is transferred, so temperature becomes the same. So at this point, temperature becomes the same, and it becomes the same such that there is no net transfer of thermal energy. No, that is total. Okay, no total transfer of thermal energy or transfer heat energy, or transfer of heat energy is actively going on in both direction at exactly same rate, at exactly same rate between the objects. Okay, so if I'm to define thermal equilibrium, I'll just simply say it occurs when different regions or objects in thermal contact are at the same temperature such that there is no net transfer of thermal energy. It's as simple as that. Or if I don't want to put such that there is no net transfer of thermal energy, I can simply say such that transfer of heat energy is actively going on in both directions. Okay, since they are acting in both directions, so it simply means they will definitely cancel out. Okay, so at exactly the same rate. Okay, so these are those points I highlighted are actually the key point in the definition. Okay, whenever you are defining the word or the term thermal equilibrium. Okay, let's see how this play out from an example right down here. Let's consider these two objects. See, this first object is 50 degrees Celsius. That is its temperature. Then this second object is actually 20 degree Celsius. This 50 degree Celsius temperature, while this was 20 degree Celsius temperature. This other was 20 degree, while this other was 50 degree. Now you could see the two objects are having different temperature, so you can't say that both of them are in thermal equilibrium at this point, that they are not in thermal equilibrium. Okay, but by the time I bring this object in contact with this other object, okay, what is going to happen is that there will be a transfer of some amount of heat or energy from this particular object to this other object. So in other words, what I'm saying is that this object will transfer heat in this direction to this other object. So there will be transfer of heat in direction when this object is in contact, or when this object is in contact with this. Okay, now when that happens, when the transfer happens, what is going to take place is that the two objects will then attain the same temperature. Okay, so at that point they become equilibrium. So how would that happen? Since this one is the one transferring to this other one and this one is gaining, so this one will gain just amount of energy that will enable it to balance up with this other one, so that both of them will now become balanced. This one will lose some amount of energy that also make it to be balanced with this other one. So in other words, if we are to look at it quantitatively, then definitely we can say that this will be losing like 15 degree Celsius temperature. So this one is losing, while this one will be gaining the 15 degrees Celsius. Just I'm just saying this. Actually, we are talking of this in terms of energy. So it's not actually the temperature, but the energy that it's losing. Okay, so the quantity of energy this will be losing will be equivalent to about 15 degrees Celsius to this other one. So at the end of the day, this one will become 35 degrees, while this one will become 35 degrees. So at that point, I can simply say that we will have something of this nature. So we have something of this nature. So at this point in time, both of them are at thermal equilibrium because they now have same temperature, due to the fact that they now maintain same internal energy. Now, to this other statement I made right here, the statement I made right here, the latter statement I made, I want to see how I can explain that using this concept that I've just explained. I'm talking of this statement. Okay, now from the statement I made, I said transfer of heat energy is actively going on in both directions. Now what that means, the point when they are at equilibrium, when they are having the same temperature, this one will tend to still transfer some amount of energy to this other one, while this one as well want to transfer energy to this other part. Okay, but since they are of the same internal energy at the same temperature, so they will likely be transferring the same amount of energy to both sides, okay, at the same rate as well. So since they are the same, let's say this one is transferring x joules, okay, this one as well will transfer x joules since they are of the same temperature. Okay, so in that case, if I find the total amount of energy transfer right here, it will equal to 0. Okay, because this one is in the positive direction and this is in the negative direction, so the resultant will give me 0. So that's why I concluded, or the definition concluded, that there is no net transfer of thermal energy. Okay, so that confirms that very statement. Okay, at this very point in time, let's see how temperature can be measured. So how can temperature be measured? We want to see how we can quantify temperature. What are the procedure, or probably what are the means by which we can measure temperature? Okay, let's take a look at that. I need to say this, that temperature can actually be measured based on a certain factor. Okay, based on a certain factor, temperature can be measured, and temperature can actually be measured by an instrument called thermometer. That one is very familiar with everyone, that thermometer is used for measuring temperature, but it is not the it is not the way the thermometer is structured that determines how it will measure, but rather what makes up that thermometer, or let me say the constituent that is used in making the thermometer, that actually determines, okay, how the temperature will be measured. Now I need to say this, that the major ingredient inside the thermometer, or let me say the major constituent inside the thermometer that will enable the measurement of temperature, okay, is actually called thermometric property of a substance. Okay, so there's a kind of substance that is imputed inside the thermometer which is sensitive, or that respond to any change in temperature, or that respond to heat. Okay, so it is the physical property of that substance inside the thermometer, okay, that tells the magnitude or the rate or how fast at which the thermometer will measure the temperature. Now, based on what I've just said now, this means that each thermometer has its unique physical property of a substance upon which it is designed. Okay, upon which it is designed, and this physical property is called thermometric property. Okay, so take note of those two words. It's very, very vital. Okay, so each thermometer has a physical property of a substance, okay, and it is on the basis of the property of the substance that the thermometer is being designed. Okay, now, and I said another word for that is actually thermometric property. Okay, now I also need to add this, that the change of the thermometric property, because every thermometric property actually varies from one thermometer to another, and they change with temperature. Okay, please, I need to take note of those two statements I've just mentioned. The thermometric property varies from one thermometer to another. This implies that each thermometer most likely don't have same kind of thermometric property or the same substance they are made of. Okay, so each thermometer, each kind of thermometer, okay, have different kind, have another kind of thermometric property. And now the thermometric property changes with temperature. Okay, so the way they respond, okay, is different with temperature. So it changes with temperature. Now I now need to say this, that the change of the thermometric property with temperature is assumed to be linear. Okay, it's generally assumed to be linear, to be straight. However, not all thermometers experience a linear change with temperature. Please, you need to let this to in the thermometric property with temperature is usually assumed to be linear. Okay, so it's meant to be linear, it's meant to be straight. But not all the thermometric property in thermometers do experience this. Some experience non-linear change with temperature. Okay, so that is a point I'm trying to drive at. Okay, so please take note of this key word: thermometric property changes with temperature. Meanwhile, not all thermometric property changes with temperature linearly. Okay, some changes non-linearly. Okay, so from here, since we are able to look at the fact that it is the thermometric property that actually determine how a thermometer will measure temperature. So at this point, we want to see different kinds of thermometer and their thermometric properties, as well as each of their examples. Okay, so let's quickly take a look at that. So we'll be looking at thermometers and thermometry properties. Okay, so here we have them. We have each of the thermometers right there. The first one is liquid in glass thermometer. Liquid in glass thermometer, and a good example is actually mercury in glass thermometer. Though we have other examples, we as well have alcohol in glass thermometer, then we have clinical thermometer. So there are so many good examples of liquid in glass thermometer. The fact is that as far as you are having something that is molten or that is in liquid form inside a glass that serves as a thermometer, then it is actually categorized under liquid in glass thermometer. Now the thermometric property of this kind of thermometer is actually the length of the liquid column. Okay, the liquid here could be mercury, and it could be alcohol, it could be whatever. Okay, so as far as it is liquid, so it is the length of the liquid column that is serving as the thermometric property for this kind of thermometer, or volume of a liquid. I mean the volume of the liquid. Okay, the volume of the liquid also serve as the thermometric property in this case. Then number 2 is gas thermometer. Gas thermometer. That's a very good example of a gas thermometer, and its thermometric property is a pressure of a fixed mass of gas at constant volume. Okay, in this case, volume is made constant while pressure is varied. Okay, as well as when the mass of the gas is constant or is fixed. Okay, so as the pressure is varied, what happens is that the temperature of the system, the temperature reading changes due to change in the pressure of the gas in the thermometer. Okay, so that is a thermometric property of gas thermometer. I'm still going to explain more on this constant volume gas thermometer as we go by. Then the next one, we have resistance thermometer. And a good example is a platinum resistant thermometer. Okay, and the thermometric property is the resistance of a coil of wire. That's one, and it will also be a thermistor, and it could also be color variation of an electrically heated wire. Okay, so it could be any of these three that could serve as the thermometric property for a resistant thermometer. Okay, so basically resistant thermometer depends on the resistance of a coil of wire or on thermistor. Knowing full well that for every thermistor have some amount of resistance that is inversely proportional to temperature. So when temperature is increased, the resistance decreases, or when the resistance decreases, the temperature increases. So it is actually an inverse variation in terms of temperature to resistance. Then we have color variation of an electrically heated wire. Okay, so all these are the thermometric property for resistant thermometer. Let's take a look at the last one right there. We have thermoelectric thermometer. Thermoelectric thermometer. In fact, this alone has explained what the thermometer is all about. Because when you say thermo, you are talking of heat. When you talk of electric, you are talking of heat source from an electric source. Heat source due to an influence of electric. Okay, so that is the way I want us to put it. Heat source due to an influence of electric. Okay, but a good example of this is thermocouple thermometer. Thermocouple thermometer, and its thermometric property is thermoelectric EMF. That is electromotive force. That is also known as potential difference. Okay, so thermoelectric EMF or effect. Electric EMF or effect. But I need to say this, that the fact that its thermometric property is thermoelectric EMF, which is electromotive force, does not mean that thermoelectric thermometer depends on power supply. Okay, so this is what we need to get to iron, although I'm still going to mention this later in the course of the lesson. But let's all know the fact that Every thermometer have its own thermometric property. Okay, from here we shall be considering temperature scales. Every thermometer has its own scale. The scale of liquid and gas thermometer could be different to the scale of resistant thermometer, and it could be different to the scale of thermoelectric thermometer. So every that has its own unique kind of temperature scale. Okay, I know the word scale shouldn't be a strange word to you. Okay, knowing full well that any instrument that is used to measure something is being calibrated in a particular scale. So the same thing goes to thermometer. Thermometer is calibrated in a particular scales. Okay, so we shall be looking at the temperature scale of some of the thermometers, and we have some of them that is having the same kind of scale. So when we take a look at one, definitely we'll be able to consider for the other. So temperature scale right here, temperature scale. Okay, what can we say about temperature scale? I've said it, for any temperature scale, for any thermometer, there is a temperature scale upon which it is being discerned. But I need to say again that for any temperature scale, there are two fixed points which are regarded as the fixed temperatures where melting and boiling takes place. You need to understand this very point. For any temperature scale, there are two fixed points. There are always two fixed points. Yeah, always 2 points, which are regarded as the fixed temperatures. As the fixed temperatures where melting and boiling takes place. Okay, knowing full well that boiling takes place at 100 degrees Celsius, so that's a fixed temperature. It is generally acceptable everywhere. Melting takes place at 0 degrees Celsius. That is generally acceptable to everywhere, which makes it a fixed temperature. So that's why we call those two values I've just mentioned fixed points. Okay, so we regard them as fixed point, and every temperature scale have this kind of two fixed points. Though it may not necessarily be 100 degrees Celsius and 0 degrees Celsius, but they have two fixed points. Now we have two types of fixed points, and these two fixed points are: number one, we have a lower fixed point. Lower fixed point, I call that LFP. LFP, which is a lower fixed point, and also regarded as ice or melting point, is actually the temperature of pure melting ice at the standard atmospheric pressure. I call it SAP, standard atmospheric pressure of 760 mm of mercury. 760 millimeter of mercury. Okay, and temperature reading at this lower fixed point is taken to be 100 degrees, since it is actually ice point or melting point, so it's taken as 100 degrees. Okay, now the second fixed point is what we call the upper fixed point, which is also regarded as UFP. Okay, UFP, which is also known as upper fixed point or steam or boiling point. Steam point or boiling point is the temperature of steam from pure water boiling at standard atmospheric pressure of 760 millimeter of mercury. Okay, so at this temperature we have the steam of pure water, meaning that water boils at this temperature, and it does that at a standard atmospheric pressure of 760 millimeter of mercury. Okay, and the temperature reading at this very given point is 100 degrees. Okay, so temperature is taken as 100 degree at this given point. So we need to take note of these two fixed points. From here, we need to know that the gap between LFP and UFP, which is lower fixed point and upper fixed point, is called fundamental interval. Fundamental interval. Okay, and the fundamental interval is divided into specific number of degrees. Okay, what do I mean? Remember, I said at lower fixed point we have a 0 degree, at upper fixed point, which is UFP, we have 100 degrees. So the interval between them is actually 100 degrees. Okay, so when we divide 100 degree, okay, into specific number of degrees, then that helps in the calibration of the thermometer. Okay, so it is like more or less saying that we are using the fundamental interval, okay, to determine the scaling of the thermometer, or the calibration of a given thermometer. Okay, so let's take note of that. Then I need to say again that it is based on this principle that we have different kind of scales. Okay, knowing full well that the lower fixed point for some thermometers may not be the same for other thermometers, but most generally lower fixed point is usually taken as a 0 degree and upper fixed point is usually taken as 100 degree for a particular kind of scale, and that scale is actually called centigrade scale. So it's actually referred to as centigrade scale. Okay, so and though I said there are other kinds of scale as well. Well, we have thermometric scale, then we have a essential scale. Okay, but on the centigrade scale, it is rated from a 0, for the lower fixed point, then for the upper fixed point to be 100 degree. Now the centigrade scale is almost related, it's almost the same to the essential scale, but I'm going to buttress this later in the course of this lesson. Okay, so let's just take it the fact that the centigrade scale is obtained from the principle of the lower fixed point and the upper fixed point, and also dividing the fundamental interval. But for thermodynamic scale, it's a complete different scale. It's an entire different scale, which is which does not have the same value at its own lower fixed point and upper fixed point. Okay, then we are going to see later how essential scale comes in and how we can even relate some of these scales together. Okay, now what I've been saying so far about temperature scale is the fact that it gives birth to the calibration of a thermometer, and I was able to say that thermometer the temperature scale of every thermometer possess two limits, two fixed points. Okay, and based on that, I can simply express that using this diagram. Just consider this diagram. This is actually a centigrade scale diagram. Okay, so at the lower fixed point I have 100 degrees Celsius. At the upper fixed point at the lower fixed point rather, I have 0 degrees Celsius. Then at the upper fixed point I have 100 degrees Celsius. Now the interval between them is the fundamental interval. So this is just the summary of what I've been saying so far about centigrade scale. Okay, now from here we want to really see the relationship between scales of different thermometers. Relationship between the scales of different thermometers. How can I relate centigrade scale to other kind of scales, okay, for other thermometer. We can actually relate the scales of different thermometers by using extrapolating method. Okay, extrapolating method. So we'll be using extrapolating method. Okay, since all scales correspond at the two fixed point. Okay, so since each kind of scale, okay, all have two fixed point, so definitely they all correspond at that two fixed point, even though most time not all of them have the same value, even though they don't have the same value at those fixed point, but they correlate as far as they have that two fixed point, upper and lower fixed point. So we can relate them based on those two fixed points. Okay, so a good example is what I have done here. Take a look at this. Here I have centigrade scale, and here I have scale of another thermometer. Okay, in this case, this represents a full centigrade scale, lower fixed point, which is 0 degrees Celsius, 0 degrees centigrade rather. Then upper fixed point is 100 degrees centigrade. Okay, this represents centigrade scale. But at this other hand, at the upper fixed point, I have RU, which means reading at upper fixed point, and here I have RL, which means reading at lower fixed point, okay, of this particular scale. Then at the middle I have reading, that is RT, which is reading at a given temperature. Reading at a given temperature, where T here on the centigrade scale is actually a given temperature on the centigrade scale, and the temperature could be in between the upper fixed point and the lower fixed point, or probably below the lower fixed point. It could be anywhere, but not at the upper fixed point and the lower fixed point. It could be in between or below it. Okay, so from here, based on the representation I have here, I can easily relate the two scales. Okay, this could be scale of any thermometer, so don't get it confused. It could be constant volume gas thermometer, it could be resistant thermometer. Okay, so it could be any kind of thermometer. So we are just using this to represent its scale, okay, and relating it with that of centigrade scale. Okay, so how can I go ahead to relate it? I want to use a mathematical expression to relate the two scales based on the representation I have right here. So let's quickly take a look at that, how to do that. Okay, so based on the diagram now, by comparing the two scales, their relationship can actually be obtained mathematically by using this relationship. Okay, by having this relationship down here. So if I compare these two, what I just need to do is to subtract the lower fixed point from this temperature, the given temperature here. Then I will divide it by upper fixed point minus the lower fixed point, and I will then relate it to what I have in this other. So what I did to this other side, what I did here is what I'm going to do here. Okay, so if I do that exactly, I will get the relationship between both of them. So what I'm simply saying is that by comparing the two scales, their relationship can be obtained mathematically as this. So it will become T minus LFP, lower fixed point, over UFP, that you are taking away LFP from it, which is the lower fixed point from the upper fixed point. Then I'm repeating the same thing at this other side. I'm repeating exactly the same thing at this other side. Okay, so that will be RT, because where I have T, I'm having RT, so that's RT, the minus the lower fixed point. Where I have at lower fixed point is RL, so I'm having RL, then all over upper fixed point, where I'm having right there is RU, so that's RU, then minus LFP, where I'm having at LFP is RL, so that's minus RL. So that's how to do the relationship right here. Okay, let's quickly look at a problem. We are going to solve a question from a particular year by using what we have gotten here. I mean, the relationship we have gotten here to solve such a problem. So let's quickly see how we can apply this expression, okay, in solving such a problem. Okay, so here is a question. This question actually was taken from May, June 2010. Okay, and here is a question. The question says, right from here, that the resistance of a thermistor at 0 degrees C, or is 0 degrees Celsius, is 3840 ohm. That's 3840 ohm. Then at 100 degrees Celsius, the resistance is 190 ohm. Then it says when the thermistor is placed in water at a particular constant temperature, its resistance is 2300 ohm. Okay, that is at a constant temperature. So we need to take note of that. That means at a given temperature, the reading of the resistance was 2300, whereas at upper fixed point, which is 100 degrees Celsius, the reading was 190 ohm. While at lower fixed point, which is 0 degrees Celsius, the reading on the other scale, which is on the resistance thermometer, was 3840 ohm. Now we are not told that, assuming that the resistance of the thermistor varies linearly, okay, with temperature, calculate the temperature of the water. Okay, and our answer is expected to be in Celsius, according to what I have here. So our answer is meant to be in Celsius. All right, so if we are to go by this, I will just apply that relationship I gave the other time. That is T, which is constant temperature, given temperature, minus LFP, then all over upper fixed point then minus LFP, that is lower fixed point, then equal to, then when I'm relating to the resistance of the thermistor now so it's going to be reading, at the given temperature or at the constant temperature, which is RT, then minus reading at the lower fixed point, which is RL, then divided by reading at the upper fixed point, which is RU, then minus reading at the lower fixed point right here. Okay, so based on what I have here, all I just need to do is to substitute, knowing full well that from the question we are asked to find the temperature of the water. Okay, to calculate the temperature of the water, that is the constant temperature, when we have the reading to be 2300. So obviously I'm asked to find T. So I'll see a way of doing that after I might have substituted the value. So T now, in this case, minus, is going to be minus 0, because at the lower fixed point of the centigrade it is 0 degree, then all over upper fixed point, that is 100 degrees, then minus lower fixed point again, that's 0, then all equal to RT, that is reading at that particular temperature, is 2300. Okay, 2300, then minus reading at the lower fixed point. Reading at lower fixed point is 3840. So I'm going to have that right now, 3840. 840 ohm. Okay, then all divided by, don't forget I'm relating it with what I'm having here. So upper fuse point at 100 degrees C is 190. So I'm going to have 190. Sorry, let me clean that. That's just a mistake. Okay. Yeah, here I go. So I have a 190. Okay, then minus at lower fuse point again, that is 3,840. 3,840. Okay, so based on what I have here, I can then do my arithmetic. If I do my arithmetic very well, all I just need to do is to simply make T the subject of the formula, since that's what I'm looking for. So if I make T the subject, don't forget 0 minus T, that's going to be T. There's 0 from 100, that's going to be 100. Then I'm taking away this from this, which will give me a negative value. Then I'm also taking away this from this, so it's going to give me a negative value. So if we are going to do that now, T is going to be, so T will equal to this minus this. So let me quickly do the calculation right now. So I'm coming, that's going to be 2300 minus 3840. So I'm having minus 15 right away from here. 40. You can confirm this using your calculator. Then don't forget that I'm having 100 there, so that's going to be multiplied by 100. So times 100. Okay. And all divided by, if I take away this from this, that's 190 minus 3,840. Okay, that's minus, I'm having minus 3,650. You can confirm that with your calculator. So negative here is going to cancel this negative out, and at the end of the day, if we do the right thing, of course minus is going to cancel a minus, or you can just use your calculation to finish the whole work. So here I'm going to be having 1,540 times 10 1,540 times 10, then divided by 365. So that's giving me 42.19. 42 point, don't forget that is a dot here, so 0.19 degrees Celsius. But you can't just leave your value like this. In Cambridge, they are expecting you to consider the highest significant figure, or probably consider also the lowest significant, the highest significant figure. So when you are approximating, you have to consider the significant figure right there. So the significant figure I'm having for degrees Celsius is 1, 2, 3. That's 3 significant figure. Okay, so I'm going to take this value to 3 significant figures. So if I do that, that is going to be 42.3. So that's to 3 significant figure. That is a value. That is the answer right here. Okay, so you can still confirm the, just as I've said, by using your calculator to do the needful. Okay, from here we proceed to the next subtopic. So from the next subtopic we're having, let's consider thermodynamic scale.
The thermodynamic scale. Now we'll be able to consider degree and centigrade scale, and I want to look at other kind of scale, which is thermodynamic scale. Okay, the thermodynamic scale actually is also referred to as Kelvin or absolute temperature scale, and is obtainable from constant volume gas thermometer. Okay, so whenever you hear me mentioning Kelvin or absolute scale, okay, Kelvin or absolute scale, temperature scale, then I'm actually referring to thermodynamic scale. Okay, now, and I say it's obtainable from constant volume gas thermometer. Now, if we are considering a rare gas, okay, for a rare gas in a constant volume gas thermometer, whenever we decrease the pressure of the gas, there's going to be a corresponding decrease in its temperature. Okay, so definitely that means for a rare gas in a constant volume gas thermometer, decrease in temperature of the gas will result into decrease in, decrease in pressure of the gas rather will result into decrease in temperature. However, at a point, the more the pressure is lowered, the more the gas behave like an ideal gas. What do I mean? As we decrease the pressure and the temperature also decreases, a point will be obtained, or a point will be reached whereby any further decrease in the pressure, okay, will cause the rare gas to be behaving like an ideal gas. And mind you, under ideal gas, it has been said that they are not realistic. It is not, they are not existing. Ideal gas don't exist, but we just assume they exist. Okay, so rare gas begins to behave like an ideal gas at a very low pressure, which will give a very low temperature. Okay, hence from this explanation I've just made, it simply means that temperature obtained at that very moment, okay, basically does not depend on any other property, okay, of a substance. It means that it doesn't depend on thermometric property, because ideal gas don't behave on any external factor of sense that you are talking of physical property of a particular substance. Okay, so it does not depend on any thermometric property at that very low pressure. Okay, so it is on this basis thermodynamic scale is being derived. Okay, so thermodynamic scale, based on my explanation so far, does not and will not depend on the property of a substance or thermometric property, but it basically depends on the property of an ideal gas. Okay, so take note of that word. Okay, I come again. I said the thermodynamic scale depend basically on the property of an ideal gas, and does not depend on the property of a substance. Okay, so take note of that word. So thermodynamic scale don't have anything to do with thermometric property or physical property of a substance. It has nothing to do with it. It only depends on the property of an ideal gas. Okay, which is only based on assumption per se, because ideal gas don't really exist. We only imagine, we only assume that it exists. Okay, so at this point in time, based on this peculiarity of the fact that thermodynamic scale don't depend on the property of a substance, okay, we can use this to distinguish thermodynamic scale from other type of temperature scales. In fact, let me say it emphatically that thermodynamic scale distinguished itself from every other temperature scale based on this unique feature or peculiarity, since it doesn't depend on the property of other substance, but other scales depend on the property of other substance. Okay, so with what I've just said, we can graphically explain this. If we consider the pressure of the rear gas, okay, to be decreased, okay, when the temperature is 100 degrees Celsius. Okay, so if we are considering the temperature of the rear gas to be decreased when the pressure of the rear gas rather to be decreased when the temperature is 100 degrees Celsius, then we can there explain this concept of thermodynamic scale using graph. So from here, let's quickly look at how we can use graph to explain the thermodynamic concept. Okay, so here I have the graph. Okay, I have P, pressure at the vertical axis, then I have temperature at the horizontal axis. Now, if I'm taking the temperature to be 100, and at this 100 degrees centigrade, Celsius, okay, I have a particular temperature, and I begin to decrease the pressure. Move where I said it the other time that decrease in the pressure of a rear gas will result into decrease in the temperature, and that's what is playing out right here. As the pressure decreases, what happens? Temperature is as well decreasing. Now, when the pressure decreases to this given point, when it decreases from here to this given point, then what happens to the temperature? The temperature becomes 0 degrees centigrade or Celsius. Okay, so at this given point, when it is 0 degrees Celsius, what we can simply say is that there's still some amount of gases. Ideally, if we are to look at it ideally, then there's still some amount of gases, okay, that can still be compressed, okay, or that we can still mount pressure on. All right, so if I now go further to lower the temperature here, at this is 0 degrees Celsius, if I reduce the temperature again, probably I reduce it until it gets to 0. So what will happen? When I reduce the pressure rather to when it gets to 0, what will happen is that the temperature will decrease up to this point. Now, that given point when pressure is further decreased to 0, okay, at that given point we'll be having a temperature tending to a value of minus 273 degrees centigrade or Celsius. Okay, so when we have 0 pressure, or when the pressure is reduced to 0, I'm having minus 273 minus 273 degrees Celsius. Actually, this particular value is just a closed value. Okay, so it's not like it is a constant value. Okay, it's just a closed value, meaning that the temperature we will likely be having when the pressure is at 0 is minus 273. Okay, meaning that it could actually be more than a little bit more than, but it can just be approximated to minus 273. Meanwhile, if we go again on further decrease of the pressure in this region, if we reduce the pressure again in a way with a negligible amount, okay, what we are going to get is a value that tends to minus 273.15 degrees Celsius. Okay, that value is regarded as what we call absolute temperature. is regarded as absolute temperature, and actually it is called the absolute temperature on the thermodynamic scale, okay, and it is taken as the lower fixed point of the scale. So what I've been saying so far is actually this, okay. On further decrease of the pressure, the temperature tends to a value of minus 273.15 degrees Celsius. So this same value is regarded as absolute zero on the thermodynamic scale. Alright, and at this given value, we can use it to represent the lower fixed point of the thermodynamic scale. So it's taken as the lower fixed point of the thermodynamic scale. Okay, so the question you may now be asking is this: what is absolute temperature? Okay, what is absolute zero temperature in a thermodynamic scale? So let's quickly look at the definition. Absolute zero of temperature is the temperature at which atoms have minimum or zero energy. Minimum or zero energy. Why do I say this? Because at this given temperature, no more pressure can be applied again. And you know, to mount a pressure on something, you require energy. It requires energy. So if there's not going to be any further pressure that can be accommodated, it simply means at this given temperature right there, which is zero, absolute zero, definitely I'll be having lowest energy or minimum or zero energy, because no more energy is going to be accommodated or can be exerted. Okay, so that is what absolute temperature. The key word here that I just need to take note is the fact that atoms in this particular temperature have minimum or zero energy. Alright, so if that is the case, and knowing full well that absolute zero is the lower fixed point of thermodynamic scale, then what is going to be the upper fixed point of this same kind of scale, of the thermodynamic scale? So let's quickly take a look at that. What will be the upper fixed point now, since we'll be able to get the lower fixed point? So the upper fixed point in this case is actually taken as the triple point of water of an agreed value of 273.16 Kelvin. Okay, this value is actually agreed on internationally. Okay, it was internationally agreed upon. Okay, so it is a value which is regarded as triple point of water, the value of triple point of water, and this is actually used as the upper fixed point of the thermodynamic scale. So the question is, what is actually triple point of water? Okay, the triple point of water is the temperature at which ice, water, and water vapor are in equilibrium. Take note of the word ice, water, and water vapor are in equilibrium. Okay, so it is the temperature at which these three terms are in equilibrium. Ice, water, and water vapor are in equilibrium. Then that we can say we are having a temperature of a triple point of water. Okay, now remember I said that the value is 273.16 Kelvin. Okay, meaning that the value is in Kelvin, unlike that of the lower fixed point, which is absolute zero, and that one is actually in degrees Celsius and degree centigrade. That is 273.15 degrees Celsius. So definitely, if I'm going to do that, I need to convert from degrees Celsius or degrees centigrade to Kelvin. So we need to take note of this whenever you are doing any calculation, you are solving any problem. So, but let's quickly take a look at what a Kelvin is. Okay, what can we define a Kelvin to be? Okay, 1 Kelvin is actually defined as the fraction 1 over 273.16 of the thermodynamic temperature of the triple point of water. Please take note of this. This is the definition for 1 Kelvin. Yeah, as simple as it is, it can be missed or omitted. Okay, because nobody knows. It can be asked in your exam to define what 1 Kelvin mean. Okay, so if you are asked to say what Kelvin mean, then this is what they actually expected from you. Is defined as a fraction 1 over 273.16 of the thermodynamic temperature of the triple point of water. Okay, now from here, let's see the relationship. We want to see the relationship between Kelvin scale and Celsius scale. Why do we want to see relationship? The reason is because the Kelvin scale is closely related to the Celsius scale, which happens to be another type of scale that replaces the centigrade scale. I don't want you to be confused. What I mean is that Celsius scale is another kind of scale which replaces the centigrade scale. Okay, so it's more or less saying that Celsius scale and centigrade scale are similar. Okay, but however, the Kelvin scale as well is closely related to the Celsius scale. So we want to see the relationship that exists between the Kelvin scale and the Celsius scale. So let's quickly take a look at that right now. Relationship. Okay, one thing we need to know about Celsius scale before we talk of the relationship between the Celsius scale and the Kelvin scale is that temperature in Celsius scale are rated in degrees Celsius. So every temperature reading on the Celsius scale is taken in degrees Celsius. Okay, so that's one thing we need to know before we start comparing the relationship between the Celsius scale and Kelvin scale. So how does Celsius scale relate to Kelvin scale? Now this is how it relates. Since each temperature obtained from Kelvin scale is measured in degrees Celsius, 1 degree Celsius can be defined just as we defined 1 Kelvin, meaning that 1 degree Celsius is defined as 1 over 273.16 of the difference between absolute zero and the triple point of water. And this is just exactly the same with the definition of 1 Kelvin. So this tells us that the Celsius scale and the Kelvin scale have similarity. Okay, now the relationship again between the temperature in Celsius scale and temperature in thermodynamic scale, which is also Kelvin scale, can be given as we have it down here. T minus small t equals to 73.15. The capital T here, the capital T right here is the temperature obtained from the thermodynamic scale, which is in Kelvin. Then the small t here is the temperature obtained from the Celsius scale, which is in degrees Celsius. So the difference between the two will give us 273.15. Okay, that will give us this difference. Okay, so this particular value is written this way. Of course, you must have come across this kind of expression before. Okay, but this is the right way of writing it. However, the relationship right here can often be approximated. Okay, can often be approximated to this t minus small t equals 273. So we can approximate the value to be 273, or you can as well rearrange what you have here just to be like this. So we can have it this way as well, which is small t. That is, you are making this subject of formula, you are making the small t subject of formula, so equal to capital T minus 273. Okay, so it's still the same thing. But note the fact that the right way of writing this expression, this particular expression, is this. This is a correct, best way of writing it. Okay, this one is just the approximated way of writing this expression, especially the value. Okay, so let's see how we can apply this formula in solving problem. So let's see a problem and see how to apply this relationship. Okay, so here we have it.
The question goes thus: the temperature of a water bath increases from 50.00 degrees Celsius to 00 degrees Celsius, rather 80.00 degrees Celsius. We're now asked to determine in Kelvin and to an appropriate number of significant figures. Okay, number one, the temperature 50.00 degrees Celsius. And if you look at the mark allocated for this question, it's just 1 mark. So you are not expected to waste time on this kind of question. Just go straight away to the point and find the value of what you are asked to find. So in this case, we're asked to convert 50.00 degrees Celsius to Kelvin. So applying that formula I gave, the formula that relates Kelvin and the Celsius together, okay, I will just say T, capital T, which is in Kelvin, equals yes, that is a T, small t, okay, plus 2, coming, we have a cleanup of this, so plus 273.15. Okay, and our small t is actually temperature in degrees Celsius, which is 50.00 degrees Celsius. So if I do the substitution, obviously I will be having 50.00 degree Celsius, then plus 273.15. So if you do the right addition, you should be getting about 323. Should be getting 323.15 Kelvin. So this is going to be the answer. So what I've done here is I made capital T the subject of formula from the relationship I gave between temperature in thermodynamic scale and that of this. Now I go to the second one. We have to find the change in temperature of the water bath. The change is actually from 50 degrees Celsius to 80.00 degrees Celsius. Okay, so and definitely this is going to be the final temperature, while this is going to be the initial temperature. So change here is going to be subtracting initial temperature from the final temperature. So
obviously I'm going to have that capital T. Don't forget our answer is to be in Kelvin, and it's just 1 mark, so I'm not expected to waste any time at all. So obviously I have to convert 80.00 degrees Celsius to Kelvin right there. And if I do that just the way I did this by applying this formula right here, okay, I'll just substitute for small t to be 80. Obviously I will be having something like 353.15. That is if I substitute for 80 and add it up. Then don't forget this change, so that is going to be minus the initial temperature, which I've already gotten here. Okay, that is going to be minus 323.15, and the whole in Kelvin. So if I do the subtraction, that is going to be 30.00. Now, why am I leaving it as 30.0? Because we are told to present our answer in the appropriate number of significant figure, and the highest significant figure I'm having is 4 significant figure. That's 1, 2, 3, 4. Okay, so this is going to be also a 4 significant figure, 1, 2, 3, 4. Then as well as this, that is appropriate number of significant figure right here. That is going to be 323.15. The reason being that from the equation I applied there, actually I'm having 1, 2, 3, 4, 5. So I'm having 5 significant figure. Okay, so to give room for the thermodynamic temperature, of course, this can be in 5 significant figure as well. Okay, so this is very appropriate as well. Okay, so from here we can quickly consider the next aspect of this topic right away.
There's an important thing to note when taking temperature reading. Okay, so I want to see important thing to know when taking temperature reading. One important thing to know is that temperature reading for an object may differ from one thermometer to another. Yeah, though I've said something similar to this before now, but I'm reiterating it again, that one important thing to note when taking temperature reading is the fact that temperature reading generally for an object may differ from one thermometer to another thermometer. Why? The reason is this. Number one, temperature scale assume linear change of particle with temperature. Temperature scale assume linear change of property rather with temperature. Okay, I've said this before that all temperature scales assume assumes a linear change with with its property. Okay, or you can just say the property of every thermometer, okay, changes linearly with temperature. Okay, it has been said before, so this is just a confirmation, and this is one of the reasons why temperature reading will always vary from one thermometer to another. Another reason is that physical properties may not vary linearly with temperature. Okay, a good example is that of thermocouple and resistance thermometer. For thermocouple, its physical property don't vary linearly, as well as that of resistance, its physical property don't vary linearly with temperature. Okay, so this point 2 justifies point number 1 right here. Okay, since temperature scale assumes linear change, okay, and not all temperature
may vary linearly, some vary non-linearly. Then number 3 is that temperature reading agrees only at fixed points of thermometer. So definitely every other point on the scale of the thermometer cannot be related or don't agree together. Every other point don't agree together. Okay, so they don't correspond. They only correspond, they only agree just only at the fixed point, which is the upper fixed point and the lower fixed point. So from here quickly, let's take a look at differences or comparison of thermistor and thermocouple thermometers. So when we see the comparison between them, comparison of thermistor and thermocouple thermometer. Now, based on the Cambridge syllabus, I shall be using both the relative advantages and disadvantages of thermistor and thermocouple thermometers to differentiate them. So I'll be using the advantages, the relative advantages and disadvantages to make a comparison of the two of them. Don't forget that thermistor is an example of resistant thermometer. Okay, while thermocouple is an example of thermoelectric thermometer. Okay, so now before I go on with a comparison, I need you to take note of this. Anywhere you see asterisk, wherever you see asterisk mark, okay, on a particular point I make, that point simply connotes the advantage of that particular thermometer. Okay, so those one without asterisk stands for the disadvantages. Okay, so in other words, as we are doing the comparison, you are also seeing the advantages of each of them as well as the disadvantages of each of them. So let's see them right here. Number 1, for thermistor, it has larger thermal capacity. Of course, that's a disadvantage. That's a disadvantage over thermocouple, because thermocouple have small thermal capacity, meaning that you just need little amount of heat supply before it takes its reading. And so in other words, it is sensitive to heat capacity, to heat supply, because just only need little amount. But for thermistor, before it can be sensitive, you need larger heat supply. Okay, so that makes it to have a larger thermal capacity. Okay, second one is that it have a fast response. Okay, it is a bit of fast response, or you can say slower response time than thermocouple. However, for thermocouple, it have a faster response or short response time, which makes it very sensitive. Okay, what does that mean? That means in relation to what I said at the first point at number 1, it shows that thermocouple responds very fast compared to thermistor. Okay, and that makes its response time to be very, very short, because it is very sensitive to heat compared to thermistor. Okay, though as take both of them, the reason because thermistor also have advantage over every other thermometer based on these attributes. Okay, so it's still a relative advantage to thermistor, but just that thermocouple exhibits more sensitivity than that of thermistor. Okay, then again, for thermistor it has narrower range, while for thermocouple it has a wider range. That means it can measure a wider range of temperature compared to that of thermistor. Then the next one, not suitable to measure varying temperature, meaning that it can only measure suitably constant temperature, not varying temperature. But for thermocouple, it is suitable to measure temperature difference or change in temperature. So in other words, it can measure varying temperature. Okay, another one again is this, which is number 5. It is larger in size or very robust, and that's a disadvantage. Okay, but for thermocouple, it is physically small or readings can be taken at a point. So it is portable in a way compared to thermistor. Then another point number 6 is that it gives accurate reading, so it is accurate. But for thermocouple, for accurate reading, a high resistance voltmeter is required. So for me to have accurate reading, I need to connect a high resistance voltmeter. Okay, but for thermistor, it gives an accurate reading. Then number 7, power supply is required. Okay, because resistor depend more on the flow of current. Okay, so power supply is actually required, but for thermocouple, no power supply is required at all. Then in number 8, it depends on physical property of a substance. Yeah, it depends on physical property because it depends on the resistor of a coil or wire or thermistor or whatever. Okay, but for thermocouple, it does not depend on physical property of a substance. Why? Because it depends solely on the property of ideal gas. Okay, from here, let's look at other advantages of thermocouple. We will be able to compare between thermocouple and thermistor. We want to see other advantages of thermocouple. And another advantage of thermocouple is that readings can be taken remotely. Readings can be taken remotely. Actually, this other advantage applies to thermistor as well, because thermistor reading on thermistor can also be taken remotely, but not like that of thermocouple. Okay, so but thermocouple can give us reading remotely with ease. Okay, let's see other disadvantages of thermocouple as well as thermistor. Okay, these disadvantages I want to mention applies to both thermocouple and thermistor. Number 1 is that non-linear variation with temperature. That is, the variation with temperature is non-linear. The variation of their physical property is non-linear with temperature. Okay, however, variation in resistance is linear for small range of temperature, but this range of temperature is actually very negligible, very small. So it's a small range of temperature. So conclusively, we can say that they still exhibit a non-linear variation with temperature. Okay, and this is the more reason why temperature reading on them will always vary from each other. Then number 2, they require calibration. Yes, thermocouple requires calibration before it can be useful, as well as thermistor. It requires calibration before it can be used to take reading. So from here, we'll be able to look at needful aspects of the topic. But meanwhile, Cambridge wants you to know how to use thermocouple to measure the temperature of a bouncing flame. Okay, of a bouncing flame. Actually, this experiment, according to the Cambridge syllabus, just wanted to have an idea of basically how to use the thermocouple. Okay, how to take reading with the thermocouple. So it's not really a serious one, but it is very good if you can just try to make further research, further findings on how to use thermocouple on to measure the temperature of a bouncing flame. Okay, so there are a series of videos that can help you to figure this out, even though you may not be capable of carrying out this experiment on your own in the laboratory, because it requires extra care. Okay, but you can as well watch some couple of videos online that will help you to understand how the experiment is being carried out. Here we'll be considering question. So we're in question time right now, and I want you to lay your hands on these following questions, to help you solidify what you have learned so far. Question is this: you can just pause the video and take a look at the question and answer them. Okay, the question number 2 is, you can pause the video and take a look at the question. The question number 3 is this. Pause the video, take a look at the question. Question 4 is this. You can pause the video and take a look and answer the question appropriately based on what we have learned so far. Then question number 5 is this. The continuation of question number 5 is this. So this continuation of question number 5. Okay, so video and answer them. Alright, so from here we come to the end of the class. It's nice having you on to this lesson, and I hope to see you in all other videos. So you can check up the next videos on other topic for you to get yourself well grounded in all the topics too. So hope to see you again in this same channel, and I admonish you try to subscribe to this channel so that anytime I upload a video, you can be the first person to have a feel of it, of the video. So it's nice having you again. See you in another lesson. Do have a nice time. Bye for now.